All right, volume, the last frontier. No. All right, so what we got going on is we're going to take things and we're going to spin them around different axes, and we're going to start trying to find the volume that is created. And we start a little bit of that with the how sweet it is when we start drawing these and on graphs and finding out the candy. Okay, so we're going to continue it. Again, we've seen this formula before, but I want to more formalize it because I never actually said it during my actual lectures here. So if I want to find any volume of a solid, okay, I need to find the area of one of my cross sections and integrate that area from A to B. So again, here are your steps. You're going to go ahead and sketch a solid. You're going to find a formula for that cross-sectional area, okay? And then you're going to find your limits of integration. And finally, you're going to integrate it. 4 easy steps. And we're going to do that today. I'm going to do 6 examples with you. And then we're going to, you have 5 on your own. All right, so here we go. Boom. So here we go. This first one here says I want to have a region of this graph. It is f of x equals 2 plus x cosine x, and the x-axis all over the interval -2 to 2. And it is going to be revolved around the x-axis. So as I discussed, the way that you guys want to be able to take or draw these is first draw the section that they are wanting us to draw. So again, here is my -2 to 2. And then the next part then is to draw the reflection of it. So here's my reflection. And then just drawing in some quick little sketch pieces. And when I draw this in, there I go. Because it's asking me to rotate it around the x-axis, which is why I draw the reflection across the x-axis. Alright, so now it's drawn that way. Then what I'm going to do is I'm going to draw my little representative ring. Okay, my cross section, if I take a bite out of it, chomp. There's my circle, and I got to ask myself, okay, how can I find the area of that circle? It's always, you always start at the center of rotation. My center of my rotation is here on the x-axis. I always start there. I move out to the side. I want that to be my radius. So this is my radius of that circle. And again, so when I'm finding my area, I need to think area of a circle is going to equal to pi r squared. If you need some help as far as visualizing, down here I have a little graphic of that for the visualization. And here you can see the little disk where this is my radius. And then how can I describe that radius in terms of x? Well, in this particular case, this radius is represented by the function f of x. So if I were to go ahead and find this, so that means that my area is equal to pi. My radius is now 2 plus x cosine x quantity squared. And now I go ahead, now I need to, so I found my area. Now I need to set my limits of integration. My limits of integration are always going to be, well, depends on which my axis is. Since I'm rotating on the x-axis, everything's going to be in terms of x. So when I rotate around the x-axis, everything's in terms of x. So I'm going from -2 to 2. Pi times 2 plus x cosine of x quantity squared dx. This is with respect to x. And now on this particular one, it'll be with a calculator, because this is not one that we can easily pull off. So I'm going to get my calculator, and we'll see what the answer is here shortly. And my answer that I got on my calculator is a 52.488 units cubed. Again, because I'm finding volume of a vase, okay, or this vase shape, so that's why it's units cubed. Now, one of the things that we had always dealt with, okay, in a problem situation is that we've always dealt with a solid piece of a cross-section, okay, in these volume problems. We've always dealt with a solid cross-section. So whether it be a trapezoid, a triangle, a circle, it's been solid. Not so with our next problem. And let's go ahead and take a look at that. Okay. So this first part here, when I sit down and I take a look, this says here, here's a region in the first quadrant enclosed by the y-axis in the graphs of y equals cosine x and y equals sine x. And it's revolved around the x-axis to form a solid. So to help us out here, that top line, since it's starting up on top, right, that's going to be our cosine x graph. The one down here on the bottom is our sine x graph. And they say it's going to rotate around the x-axis. So I want to draw that little rotation symbol there. And what you should see, again, if you're having visualization issues, well, let's first take a look here. If I were reflected around the x-axis, so reflected around the x-axis. And so there's my shape. Let's see if I can do it a little bit better. There we go. So what's being eaten out of there? What shape do I end up with? So the way I draw this is here's that solid piece there. There's that solid piece there. Okay. Actually, you can see that whole piece in there. There. And what little shape do I get now? Looks like a donut. And again, if you're having problems visualizing it, look over here. There's a 3D here, and here's a 3D model that I made. You can hopefully see the graph having a hole stuck in it all the way down. So how can I find the volume of this? It's no different. My integral part still stays the same. A to B of my area, how can I find dx? How can I find this? So let's pull my shape out. What shape do I have? It's a donut. So how can I find the area of this? I'm hoping that you say, well, if I know I can find the big circle, if I can find the area of the big circle, okay, and subtract out the area of the small circle, that would give me my area of my donut. So area of the big circle minus area of the little circle. So let's have a little bit of fun with this. So if I have area of the big circle is pi big R squared minus area of the little circle, which is a little r squared. Oops, not a. Pi little r squared. Well, couldn't I factor out a pi and just have this be pi r squared minus little r squared? And that's going to be the area of my donut. Okay. But what is my big R and what is my little r in this case? Well, let's go back. I always start at the center of my axis, or where it's being rotated, and I go to, well, the top of my big circle. This will be big R. There's big R. Well, what is that if I go from the x-axis to the top? Well, it's a function, but what function is that? Cosine of x. So in this case, big R is going to be cosine of x. And what's little r? Well, little r, again, I start at the center of my rotation. Start at the center of my rotation, and I go out. There's my little r right here. Well, again, that's going to be a function height, right? Well, what function is that going to be? Sine x. So little r is sine x. So now I have all the pieces, I believe. So I'm going to start off here the integral pi times big R squared, which would be cosine of x squared minus sine of x squared dx, and it's dx because I'm going around the x-axis. So then what's my limits of integration? Easy one is 0. But then where do they meet at? Where does sine and cosine have the same value? I'm hoping that you should know that that's going to be pi over 4. Okay. Again, I have no easy way of answering this. Okay. So it's, I can always rewrite this, right? Pi integral 0 pi over 4. So I'm going to go to my calculator, and I'm going to find out what my answer is. And this is just so you know, this is how you're going to put it in your calculator, the way it looks right here. Okay. All right, here we go. I'll pause it. Pausing. So just so you know, what I did is I took this part of my equation right here and put that into my calculator, leaving the pi out, and got an answer of 0.5 times pi. So it's 0.5 pi units cubed. Okay. Again, wow, right? Pretty intense. I mean, here I have this magic cone looking shaped thing that's got something dug out of it, and I can tell you that the shape has a pi over 2 units cubed. Mind blowing, right? Okay. So next I come over here. Boom. Now, this one doesn't have anything for it, but I'm actually just going to give this to you as a quick, hint that, or not hint, but quick little side of fun, that if my cross sections, if I have two shapes that look completely different, like this cylinder here and this cylinder is all bent out of shape, but at every level, as I go up and up and up, the cross sections, the cross sections here and here are the same. As I keep going up and up and up and up, the cross sections are the same, then my volumes are going to be the same. How crazy is that, right? I can have two completely different looking shapes, but if the cross sections are going to be the same all the way across, then my volume is going to be the same. Here's an example of that right here. Okay? Anyway, the guy who came up with it is Mr. Cavalieri. Pretty cool. All right, just a cool random thought. Next. All right, so let's get these examples pounded out and out of the way and see what it is. So it says, I'm going to do all of 29 here, and it says find the volume of the solid generated by revolving the region bound by the y equals square root of x, and the lines y equals 2 and x equals 0. Okay, so I drew up my lines right here. So here's my y equals 2. Here's my y is equal to the square root of x. And x equals 0. X equals 0 is the y-axis. And that's the region that was shaded or bounded by that. And then let's do part A. This first one's going to be part A. And I'm going to rotate it about the x-axis. Okay. So if I rotate it about the x-axis, here's my x-axis here. So if I'm going to reflect it, so again, I do that. Reflect it across like this. And then there's the rest of my shape. Just redraw that there. Okay, there's the rest of my shape. Not exactly to scale, but close enough. Okay. Boom. So what shape do I see when I rotate this? And this is going to be the part that's going to be kind of on the interesting side, is that I actually get a really big donut, don't I? Okay, so I have a really big donut that's sitting inside there. Okay, and that's what you got to be trying to think out. And the best way to figure out if you're going to have a donut or if you're going to have a circle, okay, is that with a circle, the entire area will be flush up against my axis of rotation. In this case, it is not. My axis of rotation is not flush. So what do I get? Okay, I get, so what do I get? I get a ring. So again, my formation for my ring, or the formula for the ring, is going to be the integral. Pi is on the outside. Big R squared minus the little r squared dx. Okay, and I have to find out where these meet. So if y is going to be 2, that means x is going to be 4. So I'm going from 0 to 4. Okay, so what's big R and what's little r? Again, big R goes from the center to up here. Center to up here. Center to way up here. Well, what is that distance? Oh, that's just my y equals 2. So it's always going to be 2. So it's always going to be 2. So 0 to 4, 2 squared minus, what's little r? Little r again goes from the center of my rotation to here. What's that this time? That is my function height. What's my function? Square root of x dx. So when I solve for this one I won't need a calculator for. I take my antiderivative. I have 4x minus an x squared over 2 pi, evaluated from 0 to 4, which is equal to pi times 16 minus 8 minus, plug in zeros, 0, which is equal to 8 pi units cubed. Again, pretty cool and amazing. And if all possible, go ahead and leave this in terms of pi. Okay, it's easy enough to do. You don't have to multiply out. So what's next? I'm going to do 29b. So flip to the next slide, or go to the next slide. This way you have room to draw and do this. We're going to do this about the y-axis now. When I flip this about the y-axis, there we go, like this. Now my graph gets put up against there. I draw the reflection, and now I draw my circle. It goes from here to here. Let's try that again. There. Now again, with my whole shape being flush up against my axis of rotation, what shape do I get? I get circles. So in this one, I'm going to have here the integral for pi big R squared d what? Again, I have to make the choice, and since I'm rotating around the y-axis, it's going to be dy. So I need to make sure everything's in terms of y. So instead of this being y equals square root of x, this is going to be x equals y squared. Okay. All right. And now for my limits of integration, instead of being along the x-axis, because everything's in terms of y, it needs to be in terms of the y-axis. So in terms of the y-axis, I'm going to go from integral from 0 to 2, because that's my line y equals 2, right? Pi is on the outside, big R squared. So again, what's going to be big R? That's from here to here. That's my big R. And what does that represent? That's my function height. What's my function? X equals y squared. So this would be y squared dy. Again, be able to put this into my, I'll be able to do this one. Y to the 4th dy. Take the antiderivative, y to the 5th over 5 times pi, evaluated from 0 to 2, is equal to 32 pi over 5 minus 0 pi, which will be equal to 32 pi over 5 units cubed. All right, so we're going to stop here. As you can tell, we're already 21 minutes into this, so we still have quite a bit to go. So I'm going to pause here. I'm going to break this into 2 sections so you can stop. Now, here's the deal. I've shown you everything that you need to know to start on the homework, so you can go ahead and get started on it. Okay, don't use this as an excuse. Go ahead and get started on it. Okay, but I'll just show you, have more examples ready for you tomorrow. All right.